Vardaman is a very well-known figure in our industry. She's the president and founder of Techsearch International. She's provided market research and technology trends for the semiconductor packaging industry since 1987. Co-author of How to Make IC Packages, a columnist with Printed Circuit Design and Fab Circuits Assembly, and she's an author of numerous publications. Uh, Jan is a senior member of IEEE EPS and an IEEE EPS Distinguished Lecturer. She's a member of SEMI, SMTA, IMAPS, and MEPTEC. She received the IMAPS GBC Partnership Award in 2012 and the Daniel Hughes Junior Memorial Award in 2018. Jan is an IMAPS Fellow. Before joining TechSearch, she served on the corporate staff of MCC, the first pre-competitive research consortium in the industry. With that, Jan, welcome.
Thank you, Ravi. You know, in more than 30 years in this industry, I have to say that this is probably the most exciting time I've ever seen. So I'd like to talk to you today about chiplets. And so I titled this talk, Why Chiplets? And the reason is because we are entering a new era of semiconductor packaging, nothing like we've ever seen before. And to quote from Douglas Yu at TSMC, chiplets will be a key enabler for the next 10 to 20 years. I mean, we're at a pivotal point in our industry. We're really moving from this monolithic die mindset we've been in to the multi-die MCM to the chiplet idea. And this is going to become so important as we go through some of these next designs and next nodes that you're going to continually hear about this over time. So, what's really the major driver? If you ask anybody, if you ask somebody at AMD, if you ask somebody at Intel, if you ask somebody at NVIDIA, they'll probably tell you that what is the major driver for the reason that they're talking about chiplets? Well, it's that die size has continued to increase over time for both server CPUs, GPUs, and I'd also add for, even though the chart doesn't show it, I'd add for FPGAs as well. And performance in our industry really requires more transistors. But what the industry needs is a new, more economical approach to achieve what we're trying to do with more transistors. So this is a plot that AMD made from some of their internal analysis about the reticle limit, the reticle size, and then the various introductions of server GPU and server CPU and GPU. So you can see that this has really increased over time, and it really a dramatic increase. So that's really the first reason that people are talking about chiplets. And you say, so so why do we care? Well, it's because that when we talk about fabricating a very large die, the cost continue to increase. And that's especially true when you get to 7 nanometer and more advanced nodes. The cost to fabricate that die, because of the mass cost and everything, really becomes uneconomical. So, what the industry really needs is some kind of new approach to achieve the same economic gains that we saw with scaling. Now, I'm not saying that you can't make a big old die, because you can do that. You can certainly make a big die. You can make a huge die. As Cerbis has showed us, you can make a die as big as a wafer. But what I'm saying is that for the majority of where we're going today, for server, for GPU, for FPGA applications, this is not going to work for us. The cost will be too great. So that's really what's driving our discussion. Now, there's some other things that people talk about as drivers as well. There's some disaggregation benefits, which include optimizing the node per chiplet. So you're going to do advanced nodes on the most bleeding edge, you know, logic designs on the, really the bleeding edge nodes. And you're going to design your analog portions in older nodes where it makes more sense. And also the fact that smaller die plus higher yield is going to allow you more die per wafer And this is going to optimize the cost per chiplet. And this is what really Xilinx showed us back in the days when they introduced in around 2012 or so their FPGA slices, which I would argue is a chiplet as well, because that's really a disaggregated die broken out. And those smaller dies allowed them to have much better yield at the wafer level. And that's just simply because of the large die versus small die. So also these chiplets can be bin and speed sorted. So you can really optimize performance and you can have the sale of more chiplets. It's kind of like the argument for the LEDs. You sort those high brightness LEDs and the really good ones that hit the performance when you sort them, they go into the high end lighting applications. And then those things that you'd almost want to throw away that don't make the cut, they're your Christmas tree lights. So so you sell everything you make. You just don't get the same amount of money for the high performance ones as you do for the low performance ones. So that's the idea of this binning and sorting and why you'd want to do that. Also, this finer bumper or pad pitch for higher density, and we'll talk about that, and kind of mix and match things as well. And then some people talk about improved power efficiency as a driver. So there's a lot of different reasons that are driving this. But like I said, the overall major reason is that die size. Now, what do we mean when we say a chiplet? How do we define a chiplet? Well, a chiplet is an integrated circuit block that's specifically designed to work with other chiplets to make this more complex system that basically makes use of this reusable IP. And so the chiplet is really created by partitioning a die into functions. And you're fabricating the most the logic on the most advanced nodes where you need to. But you're doing things like fabricating analog on a less expensive node where it makes more sense because you don't get any advantage of fabricating, say, an analog part into a really advanced node. So it also, as I said, gives you smaller die, higher yield. And, we really see that advantage and that anybody can plot that out. But here's the key kicker. A chiplet is a hard IP block. It's not software, it's a hard IP block, okay? And it's got to function with other chiplets so that the design is co-optimized and you just don't do the silicon in isolation. And it's really made possible by this communication between these chiplets using a chiplet interface. And today, that's mostly a proprietary design. That's like what we've seen when AMD or Intel talks about, AMD talks about their fabric. Intel talks about their communications, and they've made some of that open for a lot of people and sharing that license free. And then other people have had some proprietary interfaces, and the foundries have their own proprietary interface, like TSMC has LipCon. And so there are all these proprietary interfaces today. And so that kind of limits the chiplet use to the people that have access to the foundry that has the proprietary interface or to people that developed their own proprietary interface. But it's that communication. So think of it as the chips communicate with each other to the point where to the performance on the outside, they would appear to be a single chip. So it's a really important concept. Okay, now this really differs from our system in package or SIP or traditional MCM, is that it's a new design. It's not just pulling together different off the shelf chips. It's actually designing things so they work together. So we're not just going here and getting a piece of a chip here that has this function or a chip here that has this function and putting them all in the same package. It's really a different concept. And a chiplet is not the package. I'm going to argue that it's the design philosophy. So we have to change our mindset from this silicon-centric thinking to system-level planning and really co-design of the IC and the package. So the industry has to think about chip design in a new way. So it's a mindset change. So this idea of chiplets and this mindset change has the same impact as when the industry moved from a peripheral chip layout to area array. And some of you remember that. I mean, remember when people just couldn't get the idea of designing anything other than a chip with a peripheral layout? And look how many designs we have with area array today. So this is really a really, I think the best word for it is a different mindset. So now, what's a chiplet package? Because I'm supposed to be talking about packaging, right? So, well, there are many different package options, and you can't say that one package is the right, correct package because there's no one size fits all in this. You've got some organic substrates, including and sometimes embedded bridge. You've got some people that use silicon interposer. You've got fan out on substrate or RDL interposer. You've got 3D configurations with micro bumps or hybrid direct bonding. You've got a lot of different, concepts that you could use for this. And I've just shown a couple here at the top on the right-hand side. You can see that this is the AMD with the organic substrate. This is the Foveros stack. We did this teardown of the product that contains Foveros. You can see the compute die, the base die, and then that's on the substrate. And then this Xilinx, if you look very closely, you'll see that those are slices. So I'd argue that those are chiplets as well. Now let's look at some of these in more detail. If you look at what AMD did, they call theirs they call it an MCM concept, but it's not your parents' MCM, okay? It's a new idea. But the reason they call it that is because it's an organic substrate. And they have multiple generations of desktop and server products that are using chiplets with organic substrates. And what their idea was to split out the analog functions from the advanced 7 nanometer node. And they published a lot of papers and given a lot of presentations to explain how advantageous that was. And then these chiplets are bin and speed sorted before you assemble them on the substrate. And then you get better memory access, you minimize local latency. You can do 1, 2, 4, 8 chiplets plus the I/O chiplets, and they're attached to this organic interposer with a reasonably high layer count. Now, TSMC has proposed just recently the idea of taking their info OS, their info on substrate, as a process for a chiplet package and targeting that at AI networking or maybe edge computing. And this is an alternative to an MCM package for chiplets in that you can get smaller feature sizes, have higher density, and probably improve bandwidths. And so they've demonstrated this at a package that's like a 2.5 X reticle with a fan out area of 51 by 42 on this 110 millimeter by 110 millimeter substrate. It's got 5 RDL layers, 4 with a 22 micron line width and 1 with a 55 micron line width. And the die-to-die I/O pitch is 36 microns. So they gave a very nice paper at ECTC just recently, which is still going on online and virtual till the 17th of this month. The other idea is people have talked about using fan out or embedded bridge, many different solutions. I've pictured just a couple of here with the S-Connect from Amkor, ASE, IBM, Intel, SPIL, TSMC. Samsung has also recently introduced some concepts that could be used for the chiplet as well. The Intel embedded multi-die interconnect bridge is probably the most famous embedded bridge concept, but Amkor, ASE, IBM, and SPIL and TSMC also have embedded bridge ideas, and Samsung has actually promoted an embedded bridge idea as well. So if you look, here's the embedded bridge, and that's in a laminate substrate, and that's used for the chips to communicate down through the substrate using the bridge between those two die or two tiles, as Intel likes to call them. And Intel has also introduced the Foveros technology, which is a 3D concept. And this has where the base die, they call it the base die, uses advanced nodes, such as it could include things like power management features, voltage regulators, DC-DC converters, all kinds of things, but basically kind of analog functions. And the benefits include reduced voltage drop, power efficiency, more immediate power delivery to CPU cores, elimination of passives on the substrate, and basically system-wide communication across multiple chiplets, um, per die versus the limited die-to-die, connections. And so basically, this has been used already in production for the Samsung Galaxy Note S, a mobile to PC. And that product actually has longer lasting battery. There's no fan. It's a very thin package, so it allows a really thin product. And so in that case, in the Lakefield introduction, the CPU's on 10 nanometer, and what they called at one time an active silicon interposer, or the base die, is in a 22 nanometer node. Now, they've also introduced the idea of this co-EMIB, where you combine the EMIB and the Foveros to make a really high density solution. So you could also connect the HBM using the bridge technology, as you can see here, to the Foveros, which has the base logic, which is the less advanced nodes, with the advanced nodes connected on that. And these are the chiplets. And this is called what this is called is the tiles. And so we're going to see this introduced in Intel's upcoming data center GPU. Now, those things that I've talked about, the Foveros technology, that currently uses a microbump pitch to connect those chiplets. And that's what we've seen with mostly in the AMD versions. It's been a copper pillar. So that but the idea is that if you want to go to higher density, you want to go to hybrid bonding, because that's going to allow us to have, say, 10 micron pitch or below, in some cases 9 micron pitch, because we're not dealing with bumps or pillars. And so this has to have a really clean environment, very clean surfaces that are joined together. And some people call it direct bond interconnect, direct hybrid bonding. So call it what you like, but it's basically a bumpless bonding technology. And so that's what we're seeing moving next. And one of the examples that we've seen discussed is what TSMC has called their SOIC. So their bumpless interconnection that's targeted to the HPC applications, you would join these two chips with this hybrid bond or bumpless connection. And then you'd attach that on, say, a silicon interposer. And you could also stack those. They've demonstrated like 12 high stacks with this. And then you would put that on a substrate. The beauty of this is it gives you a lot of advantages. There's virtually no distance between those chips that are stacked together, and a very, very small bond pad pitch. So it's got really good scalability. So you can really go out there to really fine density, high density, fine pitch. So basically, the bond pad pitch is as I said, they've talked about 9 microns or less. Improved speed is one of the advantages, higher bandwidth density, and better power efficiency as measured in energy per bit has been discussed. So basically, it's this bumpless bonding process that's allowed them to get this improvement in performance, power, resistance, lower inductance, and thermal resistance. So it's a very powerful introduction. Now, probably one of the first things we're going to see in production later this year is AMD's this chip for gaming that they just introduced, and this is the prototype that Lisa Su held up basically at the end of May, first part of June, and showed the gaming performance improvement. So it's the same 7 nanometer node, but much more performance gains using this chiplet design and this 3D copper-to-copper hybrid bonding. So this will be a shipping product, I understand, by the end of the year. So we're really at the beginning of our journey. Our applications today for chiplets are server, desktop, laptop, networking, AI. We've got devices such as GPU, CPU, FPGA, and future applications we expect to see using like this technology as tablets and smartphones. And the introduction of the third-party IP block providers and some standard interfaces could really broaden this market, even much, much higher in terms of number of units than what we see today. And it really depends on how those standards can be introduced and what people can do as third-party design as well, because it all has to be integrated together. So it's, as I say, it's a very exciting time, and I'd like to thank you for the opportunity to talk with you today and present this. And I hope there's a couple of questions.
Jan, there are a couple of questions.
Okay.
Okay, the first one is from Marco. He asks, is interchip interconnect interface protocol standardization keeping the pace compared to the solutions announced so far? And how many standards exist and how many more will still emerge?
Well, there are a number of standards. As I mentioned, the AMD Infinity Fabric. I mentioned some of the communication standards that Intel has, the Advanced Interface Bus, as you well know. Um, but I think that the OSDA bunch of wires has kind of gotten a lot of attention recently. That's being proposed by. I think we have a talk later in the conference to talk about some of the standardizations and the activities. And of course, Xilinx had a standard that they developed. Samsung has its proprietary interface for its foundry customers. So they're really starting to promote that. TSMC's proprietary interface, as I mentioned, is called LipinCon. They're low voltage in package interconnect. And I think there's a lot of work to try to get standards. And like I said, we'll hear more about that today. But standardization takes a really long time. So I think until then, we're going to see this only be able to be used using these proprietary interfaces.
Fair enough. We'll take a couple more questions, Ira, and then switch to the next presentation. That sound okay? So Dave
Yeah.
has a question. He says, nice intro to chiplet technology. How do you see chip harvesting relative to chiplets?
I'm not so sure what you mean by chip harvesting. If you could clarify that a little bit.
I think he means tested, like known good
Oh, okay.
chips, if you
Known
will.
good chips. Oh, well, let me tell you, all these things assume known good die, which is a fairly incredible assumption. So, I mean, some people might say probably good die. And we had a workshop on that a while back that's probably still on the YouTube station. And one of my comments was, 30 years and we're still talking about known good die. So it's one of those things where at this stage, people are just going to assume that we got it. A fairly broad assumption. So a lot of work for the test folks to be able to produce those things.
Okay. Two quick questions, Jan. One is, with the advent of chiplets, will the need for larger than reticle packages increase?
Larger than medical packages. We certainly see that if you look at a roadmap from TSMC or Samsung. Samsung has certainly introduced some of those really large silicon interposers, as well as we've seen what TSMC is introduced. And obviously, if you have more chiplets and you have them spread out, you're going to have a large maybe interposer or a large package to put that on. So unfortunately, that's what we're still seeing.
Two more quick questions. I said one more, but I'll do two. Are the I/O interfaces standards or are they company specifications?
It looks like to me they're company specific, but maybe somebody else can comment on that.
AIB is a standard also in a way, right?
Yeah,
It's a
yeah, it's an open, it's a
it's an
standard
open standard.
available for royalty-free license.
Yeah. And then one more question. How big is the chiplet market today? We are still in the early stages, right?
Oh, very
Is
early
it
stages. I
not
mean,
yet mature,
it's
right?
a handful. It's AMD has their servers and desktops. So it's a fairly small number if you count the FPGAs, but it has the potential to grow very, very big in terms of unit volumes. And also the dollar value, but it's we're at the beginning, we're at the start, so that's why you get the hockey stick projections when you're starting off from such a small base.
Fair enough. Maybe in interest of time, Jan, we could move to the next presentation and then you and I
Uh,
can answer on the chat.
Robbie, we can take one or two more.
We can? Okay,
Okay.
good.
Yeah, yeah,
Okay. So I'll just go in sequence then. What are currently the biggest hurdles and challenges to introduce hybrid bonding?
the hybrid bonding, I asked that question to one of the speakers at ECTC, and they said the cleanliness. Because if you think about it, you've got these really, really tight pitch pads. You've got really tiny pads, and you're going to try to join those together. And if you have any kind of particles, you're not gonna get a bond. So it's the cleaning part of it that's really the gotcha. And that's why people talk about the plasma cleaning, doing this in an atmosphere, all those kind of things. So it's not as easy as it looks in a PowerPoint. Let's put it that way.
There's another good one. Do you see chiplet configurations going down to the application specific level, or are volumes too low? How do you see 3D IP being integrated?
Good questions. 3D IP, I'm not sure. Um, I haven't really studied that part yet. And I think that, you'll have, I mean, it just, like I said, we're in the very early stages and people are just wrapping their arms around this. If you go ask one of your designers in your company, how to design a chiplet design, unless they're at one of these companies I mentioned, like a Samsung or TSMC or AMD or Intel, they might look at you with a blank stare. So we're really not at the stage where people have embraced the philosophy, if you will.
Fair. What's the impact of moving to 2.5D silicon interposer for IC substrates? Will complexity go down, as in no fine lines needed, less layers, etc.?
Well, I mean, I think people ask AMD why they didn't use a silicon interposer, and Intel has said this a lot of times. I mean, silicon interposer is fairly expensive. So a company like Xilinx uses a silicon interposer because they have 20,000 connections between those slices that they're talking about. So they have no choice but to get something that has the density that's provided by silicon interposer. But if you don't have to have that density, if you don't need that density, you wouldn't use a silicon interposer. I think the whole idea with EMIB was use the bridge to connect things where you needed that density do you put the bridge. I mean, so you don't need, the whole thing doesn't necessarily need to be high density. So again, it all depends on your design, it depends on your product, and there's a lot of different factors. I hope that kind of answers the question.
Yeah. I think the question of will complexity go down, you answered correctly. I mean, completely. The last question then, have chiplets been utilized to establish a trusted execution environment, acronym TEE, or perhaps multiple TEEs with secure communications between them?
We've heard people talk about this, but I have not seen a public discussion of it.
Got it.
So,
Ira, can we take one more question, or are we at
Sure. One more.
Okay. Last year, IEEE standard 1838 was published as a test access standard for 3D stacked ICs. Standard defines test ports only by a set of test IO names and functions. Should we make a fixed layout version for chiplets?
ooh, I'm not sure I can answer that. I might defer that to some of our other experts. When you start saying the word fixed, I kind of get nervous. So it's, I mean, sometimes that's helpful, but sometimes that limits our our flexibility, if you will. So I'm going to punt that one.
Fair enough. Thank you very much. Thanks, Jan. I really appreciate it. Both the presentation was,
Thank
as always, very good, and the answers as well.
and thank you for the opportunity.
Sure.
So once again, thank our sponsors, Advantest, Amcor, and Synopsys, who made this event possible. Advantest rated the best ATE company 2021 in the VLSI Customer Satisfaction Survey of 2021. Amcor, as we heard an excellent overview from Dave as to their work, but as the leading OSAT with differentiators in the area of technology, quality, and service. Synopsys, with their vision for supplying solutions from silicon to software. And with that, I will thank everybody for joining us today. And once again, thank you for your attention and your participation. And we look forward to seeing you again tomorrow at 8 a.m. Pacific. Thank you.